There's a spacecraft that has been dead for nearly 9 years, and it is still handing scientists new discoveries faster than most active missions currently in orbit. Its cameras stopped working in 2017. Its transmitters burned up in the clouds of a planet 800 million miles from Earth. And yet, in just the last few months, researchers combing back through the data it sent home in its final hours have confirmed something about that planet's protective magnetic field that nobody expected. Something that sits on top of an entire string of other revelations quietly published over the last year about a hidden ocean that might be warm enough for life, about a moon that may have been born in a violent collision nobody saw coming, and about a halo of dust circling Saturn's rings that had been sitting undetected in plain sight the entire time anyone had been looking. This is the story of Cassini, and specifically the story of its final images and its final orbits, the ones it captured in its very last days above Saturn. And why, even now, years after the spacecraft itself stopped existing, that final dataset keeps shocking the people studying it. Stay with me, because there is also a fake photograph tied to this story that millions of people online still believe is real. And by the end of this, you will know exactly why it isn't, and exactly what Cassini actually saw instead. To understand why this final stretch of data mattered so much, you have to understand what an enormous gamble the entire mission represented from the very beginning. Cassini launched on October 15, 1997, carried into space by a Titan IV rocket, at a moment when most of the technology inside it was already considered old by the standards of the day. It carried with it a smaller probe called Huygens, built by the European Space Agency, whose entire job was to detach from Cassini once they reached Saturn and parachute down through the thick orange atmosphere of the giant moon Titan, becoming the first human-made object ever to land on a world in the outer solar system. The journey out to Saturn took nearly 7 years, using gravity assists from Venus, Earth, and Jupiter to build up enough speed to reach the ringed planet at all, because no rocket built at the time was powerful enough to send a spacecraft that heavy there directly. Cassini finally slipped into orbit around Saturn on June 30th, 2004, threading a narrow gap in the ring system on its very first pass, a maneuver so precise that a single miscalculation would have ended the entire multi-billion-dollar mission before it had collected a single piece of new data. It worked. 6 months later, the Huygens probe separated and descended through Titan's hazy skies, sending back the first ever photographs from the surface of a moon in the outer solar system, images of a landscape carved by rivers and lakes of liquid methane rather than water, a place simultaneously alien and eerily familiar. That landing alone remains, to this day, the most distant successful touchdown any human-built spacecraft has ever achieved anywhere in the solar system, a record that has stood for more than 2 decades, and will not be broken until Dragonfly itself finally reaches the same moon in 2034. What followed was 13 years of the most detailed, sustained study any planet beyond Earth had ever received. Cassini's original mission was supposed to last 4 years. It was extended twice, first through 2010, and then again through 2017, because the science kept getting more valuable the longer the spacecraft stayed in orbit. During that time, it discovered that Saturn's small icy moon, Enceladus, was venting massive plumes of water vapor and ice from cracks near its south pole, plumes that turned out to be direct evidence of a liquid ocean hiding beneath that moon's frozen shell, an ocean that suddenly made Enceladus one of the most promising places in the entire solar system to search for life. It watched storms larger than Earth itself churn across Saturn's atmosphere, including a massive, perfectly hexagonal jet stream circling the planet's north pole, a 6-sided weather pattern unlike anything ever observed on any other planet, one that scientists are still working to fully explain. It mapped the planet's rings in a level of detail no telescope on the ground could ever hope to match, revealing structures inside them that looked almost like miniature solar systems in their own right, complete with tiny embedded moons carving grooves and waves through the icy particles, spokes of dark material that seemed to hover and shift above the rings in ways nobody predicted, and gaps kept clear by the gravitational tug of small shepherd moons orbiting right at their edges. It found new moons that nobody knew existed, discovered lakes of liquid methane and ethane pooled across Titan's northern hemisphere, and used the gravitational tug on its own orbit to reveal, in 2014, that Saturn's small moon Mimas might be quietly hiding an unexpected wobble in its rotation, a clue that researchers would not fully decode for another decade. And through all of it, the spacecraft itself kept aging, running lower on the fuel needed to keep its thrusters firing and its antenna pointed reliably back toward Earth. By 2017, mission planners at NASA's Jet Propulsion Laboratory faced a decision that had no comfortable answer. Cassini was going to run out of the propellant it needed for basic maneuvering within a matter of months. If they simply let it drift once that happened, there was a real risk, however small, that the spacecraft could eventually crash into Enceladus or Titan, 2 moons now considered strong candidates for hosting life, contaminating them with hardy microorganisms that might have survived the trip from Earth on Cassini's surface, potentially corrupting any future search for genuine alien biology on those worlds for decades to come. This concern is not a minor technicality. It is a formal principle in space exploration known as planetary protection. And it exists specifically because certain resilient microbes can survive the vacuum, radiation, and extreme cold of deep space, hitching a ride on spacecraft hardware for years without dying. If even a handful of those organisms ended up on Enceladus and later got mistaken for genuine evidence of native life by some future mission, it could set back the search for real answers by generations. And nobody involved in the Cassini program was willing to take that chance with two of the most promising habitable environments ever found in the solar system. So NASA made a different choice. Rather than letting the spacecraft die quietly, they decided to send it out in a blaze of scientific value, on a deliberate, carefully engineered collision course with Saturn itself, a plan that became known as the Grand Finale. Beginning in April of 2017, Cassini started threading itself through a gap nobody had ever dared fly a spacecraft through before, the roughly 1,500-mile wide space between Saturn's cloud tops and the innermost edge of its rings. No spacecraft had ever gone through that gap. Nobody knew for certain what was actually inside it, whether it was clear open space or a shooting gallery of ring particles that could destroy the spacecraft on the very first pass. Engineers oriented Cassini's large dish antenna forward, using it as an improvised shield in case there was debris in the gap, temporarily giving up its ability to communicate with Earth during the riskiest moments of each individual dive. It survived the first pass, then it survived the second. Over the following months, Cassini completed 22 of these grand finale orbits, diving through that gap again and again, getting closer to Saturn's cloud tops than any spacecraft ever had, gathering the first ever direct samples of the planet's uppermost atmosphere and the innermost edge of its main rings. Each individual dive took the spacecraft only about 2 hours to complete, hurtling through the gap at tens of thousands of miles per hour before swinging back out on a long, looping orbit that gave engineers on the ground just enough time to check the spacecraft's health, adjust its instruments, and prepare for the next plunge roughly a week later. Every single one of those 22 passes carried genuine risk because nobody had ever definitively confirmed the gap was actually empty of hazardous debris until Cassini itself proved it by surviving the crossing. Then, on September 11th, 2017, it made one final distant flyby of Titan, using the moon's gravity to bend its trajectory one last time, setting up the exact angle needed to send it plunging directly into Saturn's atmosphere just 4 days later. What happened in those final 4 days is the part of the story that deserves far more attention than it usually gets, because this is where the actual final images come from, and it is also where the confusion online really begins. On September 13th, 2017, Cassini's narrow-angle camera captured what would become its last close views of the Saturn system. Images of the planet's rings, its swirling northern hemisphere, the small moon Daphnis carving visible waves into the edges of a gap in the rings known as the Keeler Gap, and a final look at the giant moon Titan and the icy moon Enceladus, the same moon whose ocean plumes had captivated scientists for over a decade. These were not dramatic, artistically colored portraits. They were, for the most part, monochrome, functional, scientifically precise images, exactly the kind of data a spacecraft's imaging team actually needs, not the kind of image built for a poster. On September 14th, at 12:37 in the afternoon Pacific time, a little over 16 hours before its final plunge, Cassini captured its very last photograph of Saturn itself. After that, the imaging cameras were deliberately powered down for good, not because anything failed, but because every remaining watt of power and every bit of bandwidth on the spacecraft's aging transmitter needed to be redirected toward its scientific instruments instead, the ones capable of directly sampling the atmosphere it was about to fly through. On the morning of September 15th, Cassini entered Saturn's atmosphere at over 78,000 miles per hour, and for just under a minute, its small thrusters fought to keep its antenna pointed at Earth, while 8 remaining science instruments recorded the actual composition of the planet's upper air in real time, sending that data home even as the spacecraft itself was tearing apart and burning up like a meteor, roughly 800 million miles away. Then the signal simply stopped. Inside mission control at the Jet Propulsion Laboratory that morning, engineers and scientists who had spent decades of their careers on this single spacecraft watched a screen showing the signal strength slowly weaken and then vanish entirely. The exact moment confirmed roughly 83 minutes later, once the news had finished its own long crawl back across the solar system at the speed of light. Many of them had joined the mission as young engineers back in the 1990s and were, by 2017, watching their own children grow up alongside a spacecraft that had become something closer to a colleague than a machine. There was no dramatic final message. No cinematic countdown, just a steadily fading radio signal and then silence, followed by applause in the control room. The particular kind of applause reserved for a job finished exactly the way it was supposed to be finished, on purpose, with intention, at the moment of maximum scientific value rather than a slow, uncontrolled decline. Now here is where the fake version of this story comes in, and it is worth clearing up properly, because it has been circulating for years and it genuinely fools people. A highly saturated, dramatic, glowing orange image of Saturn has been shared across social media repeatedly, captioned as the actual last photograph Cassini took before it disintegrated. It resurfaced again in a viral video in December of 2024 that racked up millions of views, and it still gets reposted regularly. That image is not real. It was never a photograph at all. NASA published it back in April of 2017, months before the actual plunge, explicitly labeled as an artist's concept, a piece of illustrated concept art, imagining what the view might have looked like from just over Cassini's shoulder during one of its grand finale dives. The real images Cassini actually captured in its final days looked nothing like that. They were far less saturated, far more subdued, monochrome in most cases, the raw, unprocessed telemetry of a working scientific instrument doing its job right up until the very end, not a glowing piece of concept art designed to look impressive on a poster. It is a small piece of misinformation in the grand scheme of things, but it matters, because the real final images, quiet, technical, and honest, are in some ways more moving than the fake one ever was. They are the last things a 50-year engineering effort ever produced, captured by a machine that knew, in whatever sense a machine can know anything, that it was running out of time. If a story like this is the kind of thing that sticks with you, go ahead and hit like on this video right now, because there is a lot more here worth sitting with, and it genuinely helps stories built on the real data reach more people than the fabricated ones do. Here's the detail that made the entire grand finale worth the risk in the first place, and it is also exactly why scientists are still finding new things inside that dataset today. Every one of those 22 dives between Saturn and its rings gave Cassini's instruments a chance to directly sample material and measure gravity and magnetic fields in a region no spacecraft had ever visited. Early analysis of the gravity data collected during those final passes revealed discrepancies compared to the leading models of Saturn's internal structure, hinting that something genuinely unexpected about the planet's interior was still waiting to be understood, a mystery that researchers are still working through years later. The magnetometer data, gathered as Cassini skimmed just above the cloud tops, found that Saturn's magnetic field appeared to have almost no measurable tilt relative to the planet's rotation axis, an extremely unusual property that actually complicated, rather than simplified, existing theories about how the planet generates its magnetic field at all, since most working models require at least a small tilt for that process to function the way scientists expected. And in December of 2025, more than 8 years after the mission ended, researchers published a new study in the Planetary Science journal built entirely on dust measurements Cassini collected during those same grand finale orbits, using an instrument called the Cosmic Dust Analyzer to sample particles above and below the ring plane. What they found was a previously undetected halo of fine dust extending out to roughly 3 times Saturn's own radius, far beyond the thin, flat plane most telescopes have ever been able to see. The particles get knocked loose from the rings by constant micrometeoroid impacts, and while most of that material eventually falls back into the rings, or gets pulled into Saturn's atmosphere, a small fraction manages to escape entirely, slowly building an extended halo of dust that nobody had confirmed existed, until a team of researchers sat down with 8-year-old archival data and finally pieced it together. That is really the pattern running through this entire second act of Cassini's story, the part that almost nobody outside planetary science circles seems to know is even happening. The spacecraft itself has been gone since 2017, but its archive, the full, raw, unprocessed record of everything it measured during those 13 years in orbit, sits permanently available in NASA's planetary data system, and researchers are still mining it constantly, using techniques and instruments and comparison data that simply did not exist when Cassini was actually operating. In November of 2025, a team led by planetary scientist Nozer Khawaja at the Free University of Berlin published a study in Nature Astronomy, built on data from a single spectacular flyby years earlier, when Cassini flew directly through one of Enceladus's icy plumes at extremely high speed. Some of the same researchers had actually published an early look at that flyby's data back in 2011, noting the presence of organic molecules, but lacking the tools to identify exactly what they were. It took over a decade of painstaking, repeated reanalysis, carefully modeling how differences in ice grain impact speed affected the readings from Cassini's Cosmic Dust Analyzer, before Khawaja's team could finally identify a much wider suite of complex organic compounds inside those ice grains, the kinds of molecules that, on Earth, are directly involved in the chemistry that builds larger, more complex biological structures. Khawaja himself pointed out something worth remembering about the entire mission. Cassini was not designed for this. It launched nearly 30 years ago, before scientists even knew Enceladus had a subsurface ocean or a south polar plume at all. Every organic molecule identification coming out of that data now is squeezed out of an instrument that was never built with this specific discovery in mind, using patience and modern analytical techniques the original mission team never had access to. That Enceladus story kept deepening throughout 2025. Just weeks after the organic compound findings, a separate team published new research showing that Enceladus appears to be releasing heat from both of its poles, not just the South Pole where the geysers were already known to be erupting, a finding that points toward a genuinely warm, dynamic ocean underneath the ice rather than a cold, static one. In warmer subsurface, oceans are generally considered far more promising environments for life to actually take hold and survive. Around the same period, researchers running supercomputer simulations of Enceladus's plumes found that the moon's geysers appear to lose less mass over time than earlier models predicted, meaning the ocean feeding them may be more stable and longer lived than scientists previously assumed. Taken together, an actively warm ocean, complex organic chemistry, and a plume system that may have been stable for a very long time, these findings from 2025 alone represent one of the strongest cumulative cases yet assembled for Enceladus being a genuinely habitable environment. And every single piece of it came from data collected by a spacecraft that had already been destroyed for 8 years by the time any of it was published. Titan, the enormous hazy moon that Huygens landed on back in 2005, delivered its own share of surprises through the same kind of patient reanalysis. For years, one of Cassini's most celebrated discoveries was the strong suggestion that Titan hides a vast global ocean of liquid water beneath its frozen, hydrocarbon-soaked surface. A study released in late 2025 revisited that conclusion using a fresh look at Cassini's older gravity and topography data, and it complicated the picture considerably, suggesting Titan's interior is probably not a single simple global ocean at all, but something structurally messier and less understood, still likely containing liquid water in some form, but distributed and behaving in ways the original models never fully captured. And in February of this year, an entirely separate team proposed something even stranger about Titan's history, suggesting that the moon itself may have been born from a colossal collision between two smaller, older moons that once orbited Saturn, slamming together hundreds of millions of years ago in an impact violent enough to have effectively created the Titan we see today, an origin story that would have been unimaginable to the scientists who first designed Cassini back in the 1990s. There is another moon in this story that deserves its own moment because its discovery genuinely surprised even the researchers who had spent years staring at Cassini's data without noticing it. Mimas is a small, heavily cratered moon of Saturn, famous mostly for its resemblance to the Death Star from a well-known science fiction franchise, thanks to one enormous impact crater covering a huge portion of its surface. For decades, Mimas was treated as one of the most boring, geologically dead objects in the entire Saturn system, a simple ball of ice with no meaningful internal activity at all. Then, in 2024, a team of researchers analyzing subtle wobbles in Mimas's orbit, wobbles first captured by Cassini years earlier, concluded that the moon is almost certainly hiding a global liquid ocean beneath its icy shell, and that this ocean is remarkably young, having likely formed sometime within the last 5 to 15 million years, an eye blink in geological terms. That finding effectively rewrote what scientists thought they understood about which moons in our solar system are even capable of hosting liquid water. Because if a small, seemingly inert, heavily cratered moon like Mimas can secretly be hiding a young ocean, the assumption that only the obviously active moons like Enceladus deserve serious attention no longer holds up. None of this came from a new observation. It came from re-examining years-old tracking data that had been sitting in the archive the entire time, waiting for someone to ask the right question of it. None of these findings came from a new spacecraft. Every one of them came from scientists returning, again and again, to the exact same archive Cassini left behind before it burned up in Saturn's clouds. If you want to see where the next reanalysis takes this story, subscribing and turning on notifications is a simple way to make sure you catch it the moment it happens. Because based on the pace of the last year alone, the next update is probably not far off. And then, just days ago, came the discovery that ties this entire story directly back to those final grand finale orbits themselves. Researchers, examining Cassini's magnetometer and plasma data from its closest approaches to Saturn, identified an unexpected feature in the structure of the planet's protective magnetic bubble, its magnetosphere, the same kind of invisible shield that deflects harmful charged particles away from a planet's atmosphere. The team found an unusual asymmetry in the boundary region where the solar wind meets Saturn's own magnetic field, something not predicted by the model scientists had relied on for years, a twist in the structure that has direct implications for how researchers interpret Saturn's bright auroras and where a violent particle accelerating process called magnetic reconnection is actually occurring around the planet. One of the researchers involved in that study put it plainly, noting that the discovery highlights just how much genuinely new science can still be extracted from Cassini's data more than 8 years after the mission officially ended. That statement alone captures something remarkable about this entire situation. A spacecraft that stopped existing in September of 2017 is still, in August of 2026, actively rewriting scientists' understanding of how an entire planet's magnetic environment behaves, using instruments that were switched off and burned away in Saturn's clouds nearly 9 years ago, feeding a discovery that has direct consequences for how future missions to any giant planet, including Jupiter, Uranus, and Neptune, might need to model their own magnetic environments before they ever arrive. It is worth pausing here to actually appreciate what an unusual situation this is in the history of space exploration. Most missions produce their major headlines while they are still active, while the spacecraft is alive, transmitting and generating fresh data every single day. Cassini's active mission absolutely did that too, discovering Enceladus's plumes, mapping Titan's methane lakes, watching Saturn's massive hexagonal storm churn at its north pole. But what makes Cassini unusual is how much of its most important science has arrived after its own death, pulled slowly and carefully out of an archive that keeps getting re-examined with better tools, better comparison data from other missions, and simply more patient, dedicated researchers willing to spend a decade squeezing a clearer answer out of old numbers. The mission's own project scientists have talked about this exact phenomenon for years, describing Cassini's dataset as a kind of gift that keeps paying out long after the spacecraft itself is gone, precisely because 13 years of continuous, close-range observation of an entire planetary system produced more raw information than any single research team could fully process in the time frame of the active mission alone. Every graduate student who picks up a small, previously overlooked corner of that archive today is effectively opening a door that Cassini itself never had the chance to walk through, using a dataset that will likely keep generating new papers for decades to come, long after every engineer who originally built the spacecraft has retired. There is no spacecraft currently in orbit around Saturn today, and there will not be one again for a very long time. The next mission actually headed to the Saturn system is NASA's Dragonfly, a car-sized, nuclear-powered rotorcraft designed to fly to dozens of different sites across Titan's surface, searching directly for the kind of prebiotic chemistry that might explain how the ingredients for life first came together, chemistry that Cassini and Huygens could only glimpse from orbit and through a single brief landing site. After years of budget replans and schedule delays that pushed its original target date back repeatedly, Dragonfly is now firmly on track for launch in July of 2028 aboard a Falcon Heavy rocket from Kennedy Space Center. And because of the sheer distance involved, it will not actually arrive at Titan and begin its work until 2034, a full 6 years after launch. Once there, it is designed to spend more than 3 years hopping between landing sites, flying like an oversized drone through Titan's thick, hazy atmosphere, using a drill and a mass spectrometer to sample the moon's surface chemistry directly, something no orbiting spacecraft could ever do. That means for the entire span between now and the middle of the next decade, everything researchers learn about the Saturn system, every fresh discovery about Enceladus's ocean, about Titan's interior, about the planet's rings or its magnetic field, will keep coming from the same source it has been coming from for the last 8 years. A dead spacecraft's archived data, painstakingly reanalyzed by people who were sometimes still in school when Cassini actually made its final plunge. That is really the honest, complete version of the story, the one underneath a headline promising shocking final images. There was no secret message hidden in Cassini's last transmission, and the actual final photographs, however striking they genuinely are not the dramatic orange fireball still circulating in fake viral posts online. What is real, and arguably far more impressive, is a 13-year mission that ended with a deliberate, carefully engineered plunge into a planet's atmosphere specifically to protect 2 moons that might harbor life. A final act of caution built directly into the mission's design, so that whatever Cassini might have carried with it from Earth could never accidentally contaminate the very worlds it had just spent over a decade convincing scientists were worth protecting in the first place. And behind that final plunge sits a scientific archive so deep and so rich that 8 years after the spacecraft itself stopped existing, researchers are still routinely finding things inside it that genuinely surprise them. A warmer ocean than expected on Enceladus, a more complicated interior than expected on Titan, a moon possibly born from a violent collision nobody predicted, a young, unexpected ocean hiding inside a small moon once dismissed as geologically dead, a halo of dust circling the rings that had gone completely unnoticed. And now, just this month, a twist in Saturn's own magnetic shield that nobody's models saw coming. Every one of those discoveries traces back to the same handful of final, frantic weeks in 2017, when a 50-year engineering effort threaded itself through a gap between a planet and its rings that no spacecraft had ever dared enter, and kept its instruments running and its antenna pointed at Earth for as long as it possibly could, right up until the very last second it had left. Think about what that actually represents. A machine built with technology already a generation old by the time it launched, traveling for 7 years just to reach its destination, operating for 13 more years once it arrived, and then, in its final 4 days, deliberately diving somewhere no engineer had ever dared send a spacecraft before, not to survive, but specifically to learn as much as possible on the way down. The images and the data are still out there, permanently archived, freely available to any researcher on the planet, and still, all these years later, nowhere close to being fully understood. Every new paper that comes out of it is really just another conversation with a machine that has been silent for nearly 9 years, a conversation that keeps somehow producing new answers. If that is the kind of story you want more of, the real, patiently verified kind, rather than the manufactured kind, sharing this with someone who has seen that fake orange photograph floating around online is a simple, genuinely useful way to set the record straight and dropping a comment with which of these discoveries surprised you most: the magnetic field twist, the Enceladus ocean, or the idea that Titan itself might have been born from a collision, genuinely helps shape which real verified stories get covered here next. There is a very good chance that somewhere in a lab right now, someone is quietly reopening Cassini's old data files, running a comparison nobody has thought to run before, looking for whatever this dead spacecraft is about to teach us next. And when that answer comes, it will almost certainly arrive the same way every other one has. Not as a dramatic press conference, but as a quiet, carefully worded paper, built entirely on numbers. A spacecraft radioed home years before anyone had figured out what they actually meant.